today's goal of this lecture. Today I will see some more example of sequence of function which had come different type in competitive exam, mostly CSIR. Okay, let's see some example of sequence of function. First example, and this type of example actually very important for not only CSIR, for all competitive exam. Let's see the first example. The following sequence of function for n greater than equal to 1 is uniformly convergent. First option, fn from open interval 0 1 to 0 1, fnx is uniformly convergent. We all of us know if fn convergent on open interval 0 1, that implies fnx converges uniformly on fx on the closed interval 0 1. X to the power n, fnx equal to x to the power n, when x equal to 0, this value is 0. When x equal to 1, this value is 1. When x belongs to open interval 0 1, this value is 0. Therefore, fnx does not converges to f pointwise continuous function. Okay, so fnx is not uniform convergent. Another method, we all of us know x to the power n, fnx equal to x to the power n is monotone increasing function. Since monotone increasing, so supremum of fnx exists equal to x to the power n exists at x equal to 1, and this value is 1. Therefore, supremum of mn converges to 1, not converges to 0. So, fn does not converges to f uniformly. So, option 1 is the right option. That means by mn test you can tell this is not uniformly convergent. Also, another method is, if fn is uniformly convergent, on open interval 0 1, that means fn is uniformly convergent f on the closed interval 0 1. Second, for n greater than equal to 1, the sequence of function fn which is defined open interval 0 1 to 0 1 such that fnx equal to x to the power n over log n plus 1, is it uniformly convergent? Here fnx equal to x to the power n over log n plus 1. And here an equal to x to the power n log n plus 1. An plus 1 over apply root test an plus 1 over an plus an. This is a to the power n plus 1 log n plus 2 times log n plus 1 an, and this value is mod a log n plus 1 divided by log n plus 2, and this is equal to mod a. And on the open interval 0, 1, this value is less than 1. So, an converges to 0. That means the sequence of function fnx converges to fx where fx equal to 0. Now I will see, is this convergence is uniform convergence? Here apply Mn test, supremum of x to the power n log n plus 1, and this supremum value exists at x equal to 1. So, since x to the power n is monotone increasing, so supremum exists at x equal to 1. So, supremum of n belongs to natural number 1 over n plus 1. This value is tends to 0 as n tends to infinity. So, fnx is uniformly convergent on the open interval 0, 1. Next, for n greater than equal to 1, the sequence of function fn from 0, 1 to 0, 1 defined by fnx equal to x to the power n over 1 plus x to the power n is uniformly convergent. Is it uniformly convergent? When 0 less than x less than 1, then x to the power n tends to 0. That imply x to the power 1 over x to the power n tends to 0. That means fnx converges to fx equal to 0 function. Does this convergence is uniform convergence? For this, consider one subsequence an equal to 1 minus 1 over n. Then limit n tends to infinity f of fn an minus f of an. This value is limit n tends to infinity 1 minus 1 over n to the power n divided by 1 plus 1 minus 1 over n to the power n. As n tends to infinity, this value tends to e, this value tends to e. That means, this value tends to e inverse, this value tends to e inverse. That means this is equal to e inverse 1 plus e inverse. So, this value is equal to 1 over e. Therefore, if we can to find one subsequence an, for this f of an does not converges to 0, therefore the sequence of function does not converges uniformly. So this is not uniform convergent on open interval 0, 1. Greater than equal to 1, fn x equal to x to the power n over 1 plus nx to the power n. 1 plus n x to the power n. This is greater than n x to the power n. Therefore, 1 over 1 plus x to the power n, this is less than 1 over x to the power n. Therefore, this is less than x to the power n over 1 over n x to the power n. This is less than 1 over n. Fn x converges to 0 not only pointwise. This is converges to 0 uniformly, because this is always less than epsilon for all n greater than equal to n. Option 4 is not true option. Here fn x equal to x to the power n over 1 plus nx to the power n is not uniformly convergent. This is the wrong option. This is also wrong option. This is not uniformly convergent. We have got one subsequence for this. This subsequence does not converges to 0. Actually, for this sequence of function, the actual theorem is fn converges to f pointwise if there exists sequence xn which is subset of a such that fn x to the power n minus f of x to the power n tends to c which is not equal to 0. Since we have got one subsequence, consider this is xnk, the subsequence xnk. Since this is not equal to 0, so fn does not converges f uniformly. I hope my all viewers have understood. This is by this subsequence test you can verify a sequence is not uniform convergent. If we can to find one subsequence for this difference does not tends to 0, then we can tell this sequence of function not be uniformly convergent. And this is the counterpositive process. By this process, if you can to find one subsequence for this difference does not converges to 0, then we can tell this sequence of function not uniform convergent. But for uniform convergent, this is not true. For this sequence of function, I will use also another method. Here I have used the subsequence test, but I will use now another method. The method fn x equal to x to the power n over 1 plus x to the power n. X belongs to open interval 0, 1. In this interval, x to the power n is monotone increasing. Supremum x to the power n over 1 plus x to the power n, this function, this sequence of function converges pointwise to fx equal to 0 function. This value is, we can write supremum 1 over x to the power n plus 1 minus 0. Since x to the power n is monotone increasing, then 1 over x to the power n is monotone decreasing. Since 1 over x to the power n is monotone decreasing, this is the monotone decreasing. 1 over monotone decreasing function, this is converges, this is monotone increasing, because 1 over decreasing imply increasing. Since this function is increasing, supremum x belongs to 0, 1, it has a maximum value at x equal to 1, and this value is 1 over 1 plus 1, this value is 1 over 2. This is not equal to 0. I hope my all viewers have understood. Okay. OL. Finally, here fnx equal to x to the power n over 1 plus nx to the power n. For this, supremum x belongs to open interval 0, 1, x to the power n over 1 plus nx to the power n. Here similar to this, x to the power n is monotone increasing. Therefore, 1 over x to the power n is monotone decreasing. We can write this as supremum x belongs to open interval 0, 1, 1 over x to the power n plus n. Since this part is monotone decreasing, so 1 over monotone decreasing is monotone increasing. So, maximum value exists at x equal to 1. And this is equal to, this value is 1 over n plus 1, and limit n tends to infinity, this value 1 over n plus 1 tends to 0. So, fnx converges uniformly to fx equal to 0 function. This is another method. This method also very easy. I hope my all viewers have understood this method also. Okay. Let f belongs to closed 0 open 1 to closed 1 open infinity defined by fx equal to 1 over 1 minus x. Let Pnx equal to 1 plus x square up to x to the power n. Then which of the following statement are true? Option 1, fx is uniformly convergent, uniformly continuous on the closed interval 0 open interval 1. Option 2, the sequence Pnx converges to fx pointwise on closed 0 open 1. Option 3, the sequence Pnx converges to fx uniformly on closed 0 say for every 0 less than c less than 1. Option 4, the sequence Pnx converges to fx uniformly on closed 0 open 1. For this, Pnx equal to 1 plus x square up to x to the power n. and limit of Pnx n tends to infinity, Pnx equal to limit n tends to infinity 1 minus x to the power n over 1 minus x. And on the interval when x belongs to close 0 open 1, this value is 1 over 1 minus x, and given this is the fx, that means Pnx converges to fx. Pnx pointwise converges to fx. This is the fx. Option 1 is fx is uniformly continuous on close 0 open 1. If we all of us know, if fx is uniformly continuous on close 0 open 1, then limit x tends to 1 minus fx always would be exist, and this value is limit x tends to 1 minus 1 over 1 minus x. This value is infinity. But if fx is uniformly continuous on close 0 open 1, then limit x tends to 1 minus fx would be exist finitely. But this limit does not exist finitely at the point 1, at the end point 1, because if fx is uniformly continuous on close interval 0 1, means this imply fx is uniformly continuous on close interval 0 1, and the limit at the end point always would be exist finitely. Okay, so this is not be, fx is not uniform continuous. Obviously the sequence Pnx converges to fx pointwise. Option 3, the sequence Pnx converges to fx uniformly on close 0 on the compact domain 0c. I will see this is few minutes later. At first I will see the sequence Pnx converges uniformly to fx. We all of us know, if each fn is bounded, then fn converges to f uniformly, that imply always f is bounded. Notice here each Pnx means P1, P2, P3 on the close interval 0 1. Notice P1, P2, P3 all be bounded function. That means each Pn is bounded, and if Pn is uniformly converged to fx, that imply f is bounded. But fx is not bounded when limit x tends to 1 minus, this value does not exist finitely, this value is infinite. So fx is not bounded. Since fx is not bounded, that means fn does not converges to f uniformly. So option 4 also wrong option. Here the sequence Pnx converges to fx uniformly on the close interval 0c. Any close interval, this is converges, this convergence is uniform convergence, because by Dini's theorem we can tell this is, because this is the closed interval, so we can apply here Dini's theorem. By Dini's theorem, on closed C, Pn plus 1 minus Pn equal to x to the power n plus 1, this is greater than equal to 0. That means Pn is monotone increasing sequence. Also, Pn converges to F pointwise on this interval, and each Pn is continuous on this interval. So, by Dini's theorem, we can tell Pnx converges to Fx uniformly. Okay? I hope my all viewers have understood. This is converges to uniformly on the closed interval 0. Okay? OL. Means option 3 also right option. Option 1 and option 4 be the wrong option. I hope my all viewers have understood how this theorem is important for sequence of function. Also MN test. These are very important. Okay? In my next video I will see more example on sequence of function. Actually, sequence of function, this topic is very important for higher study, also for any competitive exam. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.